Hi, this short video will describe how to prove continuity of operations. And the type of claim we're looking at is if f is continuous and g is continuous, then the product is continuous. You've seen such claims in 131a, and the proofs here will be very similar to that. So let's state this theorem rigorously. So what we mean by the operations of addition, multiplication, and division being continuous is that if we look at the function from R2 to R that is defined by xy is sent to x plus y, and we note this function by plus, and also the product function xy to x times y, then these functions are continuous. Now, a more technical one that I won't prove in this video, is that the division function xy to x divided by y is also continuous, but on a smaller set because it's only defined when y is not equal to 0. So you have to take away the points where y is equal to 0. Now, a remark is that, okay, this is a proof in the plane R2. However, you could look at polynomials in high dimensions. You could look at ratios, xi over xj, or generally you could look at sums of functions, divisions, and products. All of these will be continuous, assume these functions continuous in Rd, and these functions continuous if f and g are continuous. So these are analogies of these statements in the more complex cases. These ones I will discuss in our Monday lecture, but these ones you can just assume to be true and use them whenever you need them. The proofs are very identical. In fact, they could be combined by induction from the ones that we state in this video. Now, the proofs always follow a similar scheme. I want to highlight this scheme even though it should be quite familiar to you. So any proof that you do, it has a setup phase where you state clearly your assumptions, you state clearly what are fixed, you open up these for every quantifiers, and you can also state what you're trying to prove. Then there is an optional second phase. It's essential to the proof, but you don't have to write it out, or you can write it on scratch paper, is that usually you need to make some choices, but to know how to make those choices, you have to first figure out the logic of the proof. And this is sort of scratch work, which can be a little bit informal, where you estimate and anticipate what sort of bounds you do need. And based on those bounds, you choose a delta, say in the continuity statements. Similar things in other proofs is you make the choices that seem reasonable, and then you show that those choices work. So in the case of continuity, you show that if you're close enough, that is distance is less than delta, then the function value is within epsilon. Now there's sort of a cycle that often emerges, is that you make your estimates, you choose your delta, and you go to 4. But sometimes you notice that it doesn't quite work out. You correct your estimates, you choose another delta, and you go back. And you may need to do this cycle a few times, depending on how good, what experience you have and how complicated the problem is. So this is the ultimate proof will have, the 4 has to flow correctly and will be logically sound, and that depends on these choices in 2 and 3 being right. And if they're not, you may have to return to them and adjust your choices. So in general, and this is very similar to any other proof in this class, set up, think and estimate, derive an intuition, choose a delta, and show that it works. And then you're done. So let's apply this in our case. So proof of this theorem. Now we want to show that the addition is continuous, so let's investigate that first. Our setup phase now consists of fixing a point and fixing an epsilon, because we're proving the claim for every point, every epsilon. And I'll use p instead of x here because I want to reserve x for the x component. Then I do a little bit of optional thinking, the second phase, where it can be a little informal. but I choose another point and I want to estimate how can I make the distance of the addition to the distance of the addition from the addition of P small. And let's estimate this. Okay, the addition of Q is x2 plus y2 minus x1 plus y1. And I take the absolute values and I want to estimate. And well, by now you know that triangle inequality is your best friend. So we take the difference between x1, x and x2, and y1 and y2. And then we remember one of the estimates that we've discussed has become quite useful in this class is that the component-wise difference in the components is bounded by the distance of the points with the usual norms that we are using. So this is the D2 norm. It works for all the other norms as well. So this is less than the distance, this is less than the distance, so the whole thing is less than twice the distance. By the way, this is not the best bound. The best bound would be square root 2 times the distance, and involves using Cauchy-Schwarz, but you don't have to worry about that. You don't need the best bounds, you just need some bound that will work. Okay, so now we got that. We want to make this less than epsilon, so the second factor should be made less than epsilon over 2, and that's our choice of delta. It's motivated by that estimate. And then 3, we prove that it works. 4, we prove that it works. That is, we start from the assumption and we essentially repeat the calculation from 2. We take an arbitrary point. We assume that it's close enough. We apply the estimates that we did before. And then we get that because now we're using the assumption here that this is less than delta over 2, epsilon over 2, so we get less than or equal to epsilon. And the proof is complete. Now, what about the product? The product is much more complex, and the division would be even more complicated than this, and that's why I leave it. The product already indicates something. So some of it is identical to what we did before. You set up by fixing a point P in epsilon and some epsilon positive. And we want to make the distances less than epsilon. And then we do some thinking. Okay, we have our other point. We write out the difference of the product. So x2 times y2 minus x1 times y1. Now you want to estimate this difference, and the intuition that we want to use is x2 is close to x1 and y2 is close to y1. But this is only going to work if we can somehow squeeze these differences into the expression. So what we do is we subtract x1 from the first factor, and that leads to adding x1, y2 to this expression. And if we group the terms, what we get is x2 minus x1 times y2, and x1 times y1, y2 minus y1. And then triangle inequality gives us x2 minus x1 times y2, and y2 minus y1 times x1. Now the second term is actually fine, because this is fixed. So we can estimate, and the choice can depend on it. So we could estimate the second factor as being small enough. The problem is the first one. y2 is not fixed yet. And this is why the setup phase is particularly important. Anything that's not fixed, you cannot base choices on it. So this cannot be used yet. We have to estimate a little bit further. Well, let's put another triangle inequality. Let's use y2 absolute value is less than or equal to y1 absolute value, so something that is fixed, that is basically a constant, plus y2 minus y1. Using this estimate, what we get is now 3 terms. And now we want to make each of these small. We want to make this less than epsilon, so we make each of these less than epsilon over 3. Well, how do we make the first term less than epsilon over 3? Well, we take epsilon over 3 and divide it by absolute value of y, y1. And again, because it's fixed, it's permissible. But we add a 1 here because it's possible that y1 could be equal to 0. So we have to cover our bases and add the 1 to avoid that case. Similarly, the term with an x1 here as a factor, we bound by a similar choice but with x1. But then we have the product term, and that one is a little bit annoying. So how to avoid it? We want to estimate in a simpler way that one of these factors we can just estimate kind of by a trivial factor, 1, and then another factor we want to use one of these bounds that we used. So to cover our basis and to make sure that this middle factor here is also bounded, we add a bound 1. And soon you'll see how to actually use this effectively. Okay, then we show that it works. So we take a Q now as an arbitrary point, and we assume that it's close enough, distance is less than delta, with the choice that we just made. Now the calculation is exactly the same as before, so I just copy it from above. And what we get, okay, this distance here is less than y1 times the distance. This distance here is less, or the middle term here is less than the product of the distances, or the square of the distances. The last one is less than x1 times the distance. So what we're using here is that component differences in the components, x1 minus x2 is less than the distance of P and Q. This property is very useful in practice, and it's often, you use it all the time in these continuity arguments. Okay, so we know that the distance is less than delta, which is less than that. So we get the first term is less than that. The last term has a similar bound. But then the middle term, what we use is that we use 2 different bounds. Because it's a square of things, it's easier to estimate linear things. So you estimate one of these from above by 1, and the other one, you just choose one of the other bounds. Because the delta is a minimum of things, you can use any one of them that you choose. You just can't use 1 because you need to make it less than epsilon. But okay, now this term here is less than epsilon over 3. If you drop the plus 1, you cannot drop it directly because it could be 0. And the 0 case is covered by that already being small. The second term is also less than 1. And the third term here, if you drop the y1 term, all you get is epsilon over 3. And you get that that's less than or equal to epsilon over 3 and is equal to epsilon. And this completes the proof. So always the same scheme works, except that you have to make sure that each term can be bounded. So this means that often delta will be a minimum of things. If you have square terms or some more complicated expressions, you may need to cover your bases and make sure that the distance is bounded by 1. This is harmless because we anyway imagine the points as being close. And finally, the choices of epsilon, they can depend on the initial point x, and they can depend, the choice of delta can depend on epsilon and the initial point x, but it cannot depend on the new point x, new point y2, and that's why we have to be careful with the estimates, and that's why we needed to split this term into 2 parts that we can estimate easier. So these notes will be available all on Campus Wire. Thank you for watching.